Okay, previously we studied how to determine the balanced reaction equation and the energy balance equation. And today is the last part of this chapter 13. It's about how to determine the entropy balance equation. So to solve any entropy balance equation, we need to know how to determine the entropy during a chemical reaction. Okay, so to do so, we are going to use a new thermodynamic property which is called absolute entropy. This absolute entropy can be found from table A25, but this absolute entropy is only at a standard state. So the absolute entropy can be found from this table. However, these values are only valid when pressure is 1 atm and temperature is 298 Kelvin. So if you have a system that is away from this pressure and temperature, then we need to calculate entropy of a system by using this equation. So if you have an ideal gas, the specific entropy on a molar basis, which is S bar, can be calculated by this equation if you have a single material. However, if you have a mixture of multiple gases, if you want to determine the specific entropy of one component, that component can be found by this equation, the absolute entropy of that component at a given temperature. And we can use this term to determine the effect of pressure. Okay, so it's going to be universal gas constant times natural log, the partial pressure, and the reference pressure, which is going to be usually 1 atmospheric pressure. Okay, the rest of them is the same. We are going to use the same entropy balance equation we studied in Thermodynamics 1. The only difference here is how to determine specific entropy of each component. And we are going to use these equations to determine that specific entropy. There is nothing new other than this one. Okay, so based on this, we are going to solve one problem, which is about pentane C5H12. It's going to react with air. So pentane, the carbon becomes carbon dioxide, hydrogens become water, and at the inlet we have 25 degrees Celsius. That is the standard temperature. However, the pressure is 1.5 atmospheric pressure, which is greater than standard pressure. So we are going to use the previous equation to determine the specific entropy at the inlet. And the air, which is going to react with this pentane, is at different temperature, 500 Kelvin and 1.5 atmospheric pressure. So from here, we can learn how to evaluate specific entropy at different temperatures and at different pressures. And the products, which means carbon dioxide, water, and any remaining oxygen and nitrogen, they're going to exit at 1800 Kelvin, 1.5 atmospheric pressure. So you can see again another, the different temperatures from the standard temperature and pressure different from the standard pressure. So we are going to, to practice one more time how to evaluate specific entropy of the products. So that means that you need to know how to, determine the components of the products. That means we need to know how to determine the balanced reaction equation. And we are going to determine the percent excess air, which is based on what we learned in terms of balanced reaction equation, and the rate of entropy production that we can calculate it. We can calculate it by using entropy balance equation. Okay, So that's our plan. So this particular problem, we need to be able to do all three: determining balanced reaction equation, determining the energy balance equation, and the entropy balance equation. Those three areas, which are the key three areas in this chapter, we can study all of them by this one problem. Okay. By the way, I told you that the next Thursday is going to be our first exam. You will see 3 problems from the gas mixture, the moist air, and this chapter. And I told you that you will see either dehumidifier or mixing chamber from the previous chapter. And from this chapter, you may see 2 problems. One could be, the 2 problems out of balanced reaction equation, energy balance equation, and entropy balance equation. And using this problem, solving this problem, we give you an idea about how to determine the balanced reaction equation and energy balance equation and the entropy balance equation. So let's write down the balanced reaction equation first using 100% theoretical air. By the way, we have no idea about how much air is given in the reaction. So it could be 100%, 200%, or 300%. That's one thing that we need to calculate. So the basic balanced reaction equation with pentane is going to be C5H12 is going to react with air. So this air is going to be oxygen and nitrogen. The ratio between oxygen and nitrogen is going to be 1 to 3.76. 1 to 3.76. And we do not know how many moles of air are provided. Then carbon becomes carbon dioxide, and hydrogen becomes water. And since we have excess air, so we have leftover oxygen, of course, nitrogen at the end, because nitrogen is not going to react. Then let's assume that this is 100% theoretical air. Then we have 5 carbons in the reactant, so we can create 5 carbon dioxide in the product. And we have 12 hydrogen atoms in the reactants. We can create 6 water molecules. Then we can determine the number of moles required for this reaction for oxygen. So let's see. We have 2 times 5, 10 oxygen atoms in this carbon dioxide, and 6 times 1, 10 plus 6. So we need 16 oxygens required to have complete combustion. That means we have 8 molecules of oxygen, because each molecule of oxygen has 2 oxygen atoms. So 8 of them. So this is when we have 100% theoretical air. Now, if you read this problem statement, we have more oxygen than 100%. And we do not know. So let's assume that the number of moles of oxygen is going to be 8 times x. This x can be 1 if it is 100% theoretical air. X is going to be 2 if it is 200% theoretical air. Okay? We do not know the amount of air provided. then if it is 8 times X, how many moles of oxygen in the product? So to have 5 moles of carbon dioxide, 6 moles of water, we need 16. That means 8 moles of oxygen. So the remaining oxygen is going to be 8 times X minus the required oxygen, 8 times X minus 8. 8 times X minus 8 is the remaining oxygen in the product, because 8 of them have been used to create carbon dioxide and water. So the remaining oxygen is going to be 8 times X minus 8. Then how many moles of nitrogen? 8 times X times 3.76. That's going to be 30.08. 30.08. So this is the balanced reaction equation. By the way, we do not know how much airs are provided. Yes. Oh, X. My bad. You're right. So there's X here. Okay, so this is a balanced reaction equation. We do not know X. So we are going to calculate this X. Yes. 8 times X times 3.76. Now we are going to find this X. By how? There are 3 equations that we studied in this chapter. The first one is this balanced reaction equation. What is the second one? Energy balance equation. So we can use energy balance equation based on this balanced reaction equation to determine any unknown. So let's write down the energy balance equation. What is the energy balance equation? The energy balance equation is simple. If you have a steady state open system, the energy balance equation is Q dot in plus W dot in. This is from Thermodynamics 1. I'm writing the general energy balance equation for steady state open system that you studied in chapter 4, EGR456, plus M dot at the inlet. This one has enthalpy, kinetic energy, and potential energy. And energy transfer out of the system, Q dot out plus W dot out plus M dot at the exit. This one has enthalpy, kinetic energy, and potential energy. So this is what we wrote many, many times last year, right? So in Thermodynamics 2, there is no difference. We are using the same governing equation that we studied in Thermo 1. The only difference is that now we have chemical reaction. Then first of all, is there any heat transfer according to the problem statement? No, I don't think so. There's no heat transfer, so you can neglect Q. Energy transfer by work? No. Kinetic energy change? Potential energy change? No. So what is M dot H? The rate of enthalpy. H dot that goes into this combustion chamber should be the same as M dot H, the rate of enthalpy at the exit. So this is the energy balance equation. we can use for this problem. Since there is no heat transfer and there is no energy transfer by work, we can neglect kinetic energy change and potential energy change. Then, how can we determine H? When you have a chemical reaction, this H can be determined by N times the enthalpy of formation plus delta H bar. Do you remember that we studied last week, right? So we are going to calculate this one for each reactant and each product. That's all. So let me write down H of each term. First, pentane. Gonna be, by the way, we have a dot on top of it. So this is rate of enthalpy. So the rate of enthalpy can be determined by N dot the enthalpy of formation plus delta H. So similarly, here we have a pentane in the reactant. So we have N dot the enthalpy of formation plus delta H bar. This is for pentane. And we have one more oxygen. N dot the enthalpy of formation and delta H bar. This is for oxygen. And we have N dot the enthalpy of formation, delta H bar. This is for nitrogen. It's gonna be how many components in the product? 1, 2, 3, 4. So the same thing. N dot the enthalpy of formation plus delta H bar. This is for carbon dioxide. N dot the enthalpy of formation plus delta H bar. This is for water. And N dot the enthalpy of formation plus delta H bar. This is for oxygen. And N dot the enthalpy of formation plus delta H bar. This is for nitrogen. So this is the energy balance equation for this reaction. Before we find each component, each term in this equation, there's water. When there's a water, you need to determine the phase of this water, because the properties of liquid water are different from the properties of water vapor. So you need to determine whether it is liquid water or water vapor or a mixture of liquid water and water vapor, which is the worst case, right? So what is the condition? 1.5 atmospheric pressure. And what is the temperature? 1800 Kelvin. What is the phase change process of water at this extremely high temperature? Superheat vapor. Of course, you can make PV diagram or TV diagram to determine the phase change process, but you can see at this low pressure, the saturation temperature is close to 100 something, right? So when the temperature is 1800 Kelvin, there's no way the water exists as liquid. So it's a water vapor. I'm going to say G, yes. Then let's determine, each term one by one. First, let's go with this N dot. What is the N dot of? When you solve this one, we need to make an assumption. So we are going to assume that the molar flow rate of this pentane is 1 kilomole per second. So this is our assumption. 1 kilomole per second. Then what is N dot for oxygen? 8 times X. What is N dot for nitrogen? 8 times X times 3.76, which is 30.08X. N dot for carbon dioxide, 5. N dot for water vapor, 6. N dot for oxygen in the product, 8 times X minus 8. N dot for nitrogen, this one, 30.08 times X. So we have X in this energy balance equation. Now, let's determine the enthalpy of formation for each component. How do we determine enthalpy of formation? You go to table A25. Here, the enthalpy of formation is here. The first 4 components, carbon, hydrogen, nitrogen, oxygen, the enthalpies of formation of these 4 are 0. So do we have carbon, hydrogen, nitrogen, oxygen? We have oxygen and nitrogen. There's oxygen, there's no enthalpy of formation. There's nitrogen, there's no enthalpy of formation. There's oxygen, there's no enthalpy of formation. There's nitrogen, there is no enthalpy of formation. Now, let's determine the enthalpy of formation values for the other components, pentane, carbon dioxide, water vapor. Pentane, this number, carbon dioxide, this number, and water vapor, this number. So let me write these 3 here. First, pentane minus 146,440 kilojoule per kilomole. Carbon dioxide minus 393,520 kilojoule per kilomole. Water vapor minus 241,820 kilojoule per kilomole. So that's everything about the enthalpy of formation, the enthalpy values of formation. Now let's find delta H. Delta H is the difference in specific enthalpy between the standard temperature and the given temperature. So if the substance is at the standard temperature, then we don't have to consider delta H, right? So what is the temperature of pentane? 25 degrees Celsius. So that is the standard temperature, right? So we don't have to consider delta H for pentane because the temperature of pentane is the standard temperature. What about oxygen in the reactant? This one. What is the temperature of oxygen? Air entering at 500 Kelvin is not the standard temperature. So we need to determine delta H. So this one for oxygen, what is the given temperature? Delta H at 500. What is the standard temperature? Delta, H bar at 298. So that's what we need to determine for oxygen. What about this nitrogen? Also at 500 Kelvin. So we need to consider delta H bar. This one can be determined by H bar at the given temperature 500 Kelvin minus H bar at the standard temperature 298. And where can we find these values? From table A23. So from this table, where is oxygen? This one is oxygen. This one is nitrogen. So what is H bar at 298? At 298, oxygen is going to be 8,682. Nitrogen is going to be 8,669. So let me write these two values here. For oxygen, 8,682. For nitrogen, 8,669. Then H bar at 500. So there's a 500, the last row, and H bar at 500 is this one, 14,770. H bar of nitrogen at 500, 14,581. So these two values, let me write them here. 14770, 14581. So that's how we determine delta H bar for the oxygen and the nitrogen in the reactants at 500 degrees Celsius. Now, delta H for carbon dioxide, delta H for water, oxygen, nitrogen. What is the temperature of the product? 1800 Kelvin. That is different from the standard temperature, 298. So we need to calculate the delta H bar for everything in the products because they are not at the standard temperature. So I'm going to start with this carbon dioxide first. Then water vapor, then oxygen, and then nitrogen. So this one is H bar at 1800 minus H bar at 298. H bar at 1800 minus H bar at 298. H bar at 1800 minus H bar at 298. H bar 1800 minus H bar 298. So where can we find these H bar? From the same property table, table A23. In this table, we have carbon dioxide. First one, carbon monoxide. We don't have one. Water vapor, this one. Oxygen, this one. Nitrogen, this one. So at 298 degrees Celsius, H bar for carbon dioxide is 9,364. This one, 9,364. For water vapor, 9,904. 9,904. For oxygen, 8,682. For nitrogen, 8,669. So that's how you find H bar at 298 Kelvin. Then what is the temperature at the exit? 1800. So let's find 1800. Now there's 1800 degree Kelvin. So at this temperature, H bar of carbon dioxide is 88,806. And this is for water, this is for oxygen, and this is for nitrogen. So I'm going to write these four numbers here, 1, 2, 3, 4. I'm sorry, 88,806, 72,513, 60,371, 57,651. So in this energy balance equation, we have all the values but X. So can you determine X? Yes, you can. So from this energy balance equation, this X is going to be 1.754. So that means we provided 175.4% theoretical air. That's how you solve this energy balance equation. If I give you this problem in your first exam, can you solve it? Yeah, if I give you 1 hour, but you need to solve 3 problems in an hour. So now you see, how you're going to prepare the first exam. There is nothing new. Every problem you will see in the first problem are similar to what we did in the classroom or in the homework assignments, okay, with the different numbers. There's no surprise. Everyone can get 100% if you put enough effort, okay? It's just a matter of, how much time you spend, to practice those problems. It just takes time. There's nothing difficult here, okay? The only difference between Thermodynamics 1 and Thermodynamics 2 is this term. So we have this extra term to determine the rate of enthalpy, okay? This is the only new from the energy balance equation you studied from Thermodynamics 1, okay? Of course, in your first exam, I will do my best to minimize the number of components in the equation. For example, maybe I can say we have 100% theoretical air. Then you can neglect oxygen in the product. What if I say there is only oxygen, there's no nitrogen? Then you can neglect this one, neglect this one. If it is 100% theoretical air, you can neglect this one. What if I say the fuel is not pentane but carbon? Then there's no water. So there are many ways we can save time. So read problem statements carefully when you are in the first exam, okay? Okay, so that's how we calculate the percent excess air, and let's determine the rate of entropy production. So once you know the amount of air provided in the reaction, then now you can solve entropy balance equation. So let's do that. To solve entropy balance equation, what we need to know? We need to know how to write entropy balance equation. Then how can we write entropy balance equation? It's simple. Everything is based on what we learned in Thermodynamics 1. What was the entropy balance equation for steady state open system? Entropy transfer. The rate of entropy transfer goes into a control volume plus the rate of entropy generation is going to be the rate of entropy transfer from the control volume to the outside. Then what kind of entropy transfer into a system? It can be either heat or mass. By the way, it says it is well insulated. So there is no heat transfer. So the only entropy transfer can be done by mass. So entropy transfer at the inlet. Then how can you determine entropy transfer at the inlet? N dot times specific entropy, S bar. That's how you determine entropy transfer that goes into a control volume. What about entropy transfer out? The same thing, N dot times specific entropy. Then let's complete this entropy balance equation for this balanced reaction equation. First, we have pentane. N dot of pentane, C5H12 times specific entropy of pentane plus N dot of oxygen times entropy transfer, S dot of oxygen plus N dot of nitrogen times entropy, specific entropy of nitrogen plus entropy generation, S dot gen. This is what we want to determine. I'm telling you, there is nothing new. Everything is the same as what we studied in Thermodynamics 1. The only difference is that now, the finding each component is slightly, different because we have reaction. Then, how many components? 1, 2, 3, 4. And that, the first one, carbon dioxide. Carbon dioxide times specific entropy of carbon dioxide plus N dot of oxygen times specific entropy of oxygen. I forgot water. Plus N dot of water vapor times specific entropy of water vapor plus nitrogen. N dot of nitrogen times specific entropy of nitrogen. Then what is this N dot? We assume that this N dot is going to be 1 kilomole per second. Then what is N dot for oxygen? 8 times X. Oh, by the way, we found X. Where is it? 1.754. I'm going to write it here. X is 1.754. So N dot for oxygen is going to be 8 times 1.754. N dot for nitrogen, 30.08 times 1.754. N dot for nitrogen, 5. and that for water 6, and that for oxygen 8 times 1.754 minus 8, and that for nitrogen 30.08 times 1.754. And now, how we can determine S bar? S bar can be determined by this equation. S bar degree, absolute entropy can be found from the last column of table 825 minus gas constant, natural log, partial pressure over reference pressure. So this equation, let me write it here. S bar is going to be, for I component, is going to be S bar degree, absolute entropy of I component, minus gas constant, partial pressure of this component, which is mole fraction times pressure, divided by reference pressure. So let's find this one first. S bar of pentane. How can you find it? S bar degree of pentane, which is the absolute entropy, minus gas constant times this one, YIP over reference pressure. Okay, how do we determine this one? Absolute entropy from table 825. Here, table 825, where is pentane? This one, what is absolute entropy? Where is it? This one, 348.4. Unit is kilojoule per kilogram, kilomole Kelvin. 348.4. 348.4 kilojoule per kilomole Kelvin. What is the gas constant? R bar is always 8.314. What is the reference pressure? This value has been found at 1 atm. 1 atm. What is the pressure of pentane? At the inlet, 25 degrees Celsius, 1.5 atmospheric pressure. 1.5 atmospheric pressure. What is the partial pressure of this? What is the mole fraction of this pentane? What is the mole fraction of pentane? So we have one inlet where pentane goes in, and this one is 25 degrees Celsius. We have another inlet where air goes in, 500 Kelvin, and we have one exit, everything comes out, which is 1800 Kelvin. So what are the components in this inlet? How many components in this inlet? 5, 6, 7, 2000, plus 1. There's only pentane. So what is the mole fraction of pentane at this inlet? 25, 1. So here, this Y is going to be 1. then this is going to be 345.029 kilojoule per kilomole Kelvin. So this number goes in here. Now, that was simple because there was only pentane in that inlet. Now let's talk about the other inlet. The other inlet is at 500. We have air. So let's talk about this one. S bar of oxygen, and what is the temperature? 500 Kelvin. So how do we determine that? The same rule. S bar degree of oxygen, but this one is at what temperature? 500 Kelvin minus gas constant R, mole fraction Y of oxygen times the pressure at the inlet divided by the reference pressure, which is 180 M. Then, how do we determine this absolute entropy of oxygen? Table A23. At 500 Kelvin. Table A23. Oxygen and absolute entropy is the last one. What is the temperature? 500. So what is the value that we are looking for? 220.589. This one is at 500. 220.589. 220.589. What is the gas constant? Always 8.314. What is the pressure at this inlet? Air entering at 500 Kelvin, 1.5. 1.5 atmospheric pressure. What is the pressure from the table? 180 M. What is the mole fraction of oxygen? In this inlet, we only have air, that means oxygen and nitrogen. What is the ratio between oxygen and nitrogen? Oxygen and nitrogen. 1 to 3.76. In other words, 21%, 79%. So the mole fraction of oxygen is going to be 21%. That is 1 to 3.76, the same ratio. Okay. So 0.21 is the mole fraction. 0.21 is Y of oxygen. Then you can determine the specific entropy of oxygen at 500. You get 230.193 kilojoule per kilomole Kelvin. I only have 21 minutes. So how many to go? 1, 2, 3, 4, 5. So 4 minutes each. So nitrogen this time. Oh, I'm sorry for this long arrow, but that's all I can do. I wish that the screen is from here to the end, but I don't have that. I'm going to buy a lottery today. So if I win, I'm going to install a screen. Really? Why? Oh, there are many, many lotteries. The Mega Millions, good. Powerball is good. Lotto Michigan, not bad, not good. So if I win Lotto Michigan, then I can install screen. That's all, right? So S bar degrees, so the absolute entropy for nitrogen at 500 Kelvin minus R bar Y of nitrogen, P over P reference. We already did, this is the third time that we are working on this equation. So now you get the idea. How do we get this absolute entropy? From table 823. Are you all talking about lottery? Let's talk about absolute entropy. The absolute entropy at 500, where do we find it? The same table, 823. The same table, 823. Nitrogen is the last one at 500. Absolute entropy is 206.630. 206.630. What is the gas constant? Again, 8.314. And what is the mole fraction? The ratio between oxygen and nitrogen is going to be 21%, 79%. So 0.79 is the mole fraction of nitrogen. 0.79. And what is the pressure at the inlet? 1.5. What is the pressure from the table? 1. So you get specific entropy of nitrogen 205.219 kilojoule per kilomole. Four more to go. Don't hate me because of this problem, okay? This is how we solve thermodynamics, okay? So we have carbon dioxide, oxygen, water, nitrogen. Let's do all of them together. S bar for this time, carbon dioxide. What is the temperature at the exit? 1800. 1800 Kelvin. S bar of the second one, water. 1800. S bar, the third one, oxygen. 1800. S bar for nitrogen. Can you see the last one? Yeah, you can see. 1800. How do you find these values? The same equation. Absolute entropy. Absolute entropy. 1800. 1800. Absolute entropy at 1800. Absolute entropy at 1800. Plus, minus gas constant, minus gas constant, minus gas constant, minus gas constant times partial pressure. So the mole fraction of carbon dioxide times pressure at the exit divided by reference pressure, which is 1 atm. Y of water times pressure divided by reference pressure. Y of, what is this one? Oxygen times pressure divided by reference pressure. Y of nitrogen times pressure divided by reference pressure. Whew. So how do we determine these absolute entropies? From table 823. This time the temperature is 1800. At 1800, the first one, carbon dioxide, 1800, absolute entropy is this one, 302.884. 302.884. Water, this one, 209.262. 259.262. And oxygen, this one, 264.701. 264.701. Nitrogen, 1800. 248.195. Gas constant. I don't have to write them anymore, right? 8.314. I will do that. 8.314. 8.314. Oh, I'm not going to write it here. We all know that. What is the reference pressure from table 823? 1. 1. 1. 1. 1. What is the pressure at the exit? 1.5 atm. 1.5. 1.5. 1.5. 1.5. Then the mole fraction of each component. How do you find the mole fraction of each component? The number of moles of that component divided by total number of moles. So this one. The number of moles of this component, 5, divided by the total number of moles. 5 plus 6 plus, wow, 8.1754 minus 8 plus 30.08 times 1.754. You don't like this problem, right? Me neither. So water, 6. 6 divided by 5 plus 6 plus 8.1754 minus 8 plus 30.08 times 1.754. Now oxygen. Oh, where's oxygen? This one. 8 times 1.754 minus 8 divided by, do I have to write it again? Yeah. 5 plus 6 plus 8.1754 minus 8 plus 30.08 times 1.754. One more to go. What is the number of moles of nitrogen? 30.08. 30.08 times 1.754 divided by the total number of moles. We have 12 minutes. Oh, we did on time. 5 plus 6 plus 8.178 times 1.8 times 8 times 1.7 8 times 1.8 times. Don't make this mistake in your exam. 1.754 minus 8 plus 30.08 times 1.754. We got them all. So let's find this one. We have only one unknown. So that is 3,601.24 kilojoule per Kelvin. Again, the same entropy balance equation. It just takes not forever, a lot of time to determine each property. Again, there's nothing difficult. Just it takes a lot of time to evaluate each component in that equation, but the equation is not that difficult, right? It is just entropy transfer in plus entropy generation. The rate of entropy generation is the rate of entropy out of the system. That's all. And we just determine S in and S out from the balanced reaction equation. So the key is going to be, if you are not able to determine the balanced reaction equation, you cannot solve energy balance equation, entropy balance equation. So you should be, very careful when you are determining, when you determine balanced reaction equation. So that means if you want to save time, if you want to solve everything in time, I just need to give you a simple balanced reaction equation. But this one is, the balanced reaction equation is very ugly, so that's why it took a long time, okay? So this one. That completes chapter 13, the entire Thermodynamics 2. So we are going to have our first exam next Thursday. There are 3 problems. one from gas mixture, moist air, but there is possibility you may see a sub-problem in the first problem that will ask you to determine dew point temperature. So that's 30% of your first exam. And there are two more problems from this chapter among three: balanced reaction equation, energy balance equation, entropy balance equation. But if you want to determine, if you want to solve energy balance equation, you should be able to determine balanced reaction equation. So you can, show that there should be at least one balanced reaction equation. Okay. Any question? Yes. Enter key?
Like you were taking it.
To solve one problem?
I assume you've done the answer key for the exam.
Yeah. Within time. I'm pretty sure that at least 10% will get 100% in this classroom. At least 100%, and 10%. So I hope that it goes up to 100%. Any question? Yes. I can spend maybe 20 minutes to review, the gas mixture and combustion. Okay. So you can prepare one page. You can prepare, the one page formula sheet. You can write anything front and back. Okay. You don't have to submit your own formula sheet. Make a good one and laminate it, and then use it when you go to your career. So whenever you need to, analyze thermodynamically, don't read 1,000-page textbook, but just come up with this one-page formula sheet that can guide you, how to solve thermodynamics. Okay. One hour, 3 problems, and there is a possibility that first problem has a sub-problem that will ask you to determine dew point temperature. That's all. Thank you.